We're here going to talk about some aspects of the PEnDAR project. PEnDAR is an acronym for Performance Insurance by Design Assuring Requirements. This is the first webinar for our focus group.
Sorry to interrupt, Peter. Can you just change your screen share window? We're seeing your desktop.
Oh, I'm sorry.
Excellent, thank you.
Okay, that removes distractions. Okay, so let me say a little bit about the PEnDAR project. This project has arisen really because in our kind of day-to-day work we've observed a lot of cost-performance hazards that only become visible quite late on in the development of various projects, sometimes too late for the project to be saved. And this, in our experience, is a multi-billion-dollar problem worldwide. So what we're looking into is how to enable validation and verification of cost and performance as opposed to simply functional aspects of the system. And to do this for distributed and hierarchical systems with hopefully tools that are easy to use but under the hood quite sophisticated, with the aim of supporting both initial development of some new product or services and also its maintenance during life and on ongoing incremental development. So what we're aiming to do is to provide early visibility of these cost performance hazards, so avoiding these costly failures and maximizing the chances of successful and in-budget delivery of acceptable end-user outcomes. So the partners in this project are ourselves who are speaking. We are Predictable Network Solutions. We're working together with Test and Verification Solutions, who have particular expertise in test and verification issues in safety critical systems, automotive and so forth, and Vodafone Group, who are obviously a well-known multinational company, and from the perspective of the project, they perform the role of a systems of systems integrator. They're trying to deliver innovative products and services, sometimes across very wide geographies, and they have an interest in improving the ways that they can do that. So this whole project is supported by funding from Innovate UK, for whom we're very grateful, and that's enabling us really to do this feasibility study of how these kind of techniques could be brought into more general use in the industry. So we've invited many of you to join the focus group for this project. So one aspect of what we're doing here is to run a focus group, and really this is an opportunity to articulate some of the things we know about really the laws of the distributed world or the distributed computing world, to see where the boundaries of the possible are. The problems of many projects is that they step outside those boundaries without realizing it, and then to know where those boundaries are and how to push the envelope in the way that benefits you most, how to do innovative things without risking getting your fingers burnt, and to get some insight into the way this is all developing, understanding about achieving sustainability and viability of potentially large and complex developments, and see where some of the competition might be coming from in the future. What we're hoping to get as a project, what we're hoping to get out of this focus group is to help us find out in which markets or sectors the benefits of applying these kind of techniques might outweigh the costs of adopting them. We'll say a bit more about that later. And indeed, which in your view actually are the major benefits, which are just nice to have. Your view of this may differ from ours, and really to get some feeling for how such a methodology could be consumed. Is it a matter of packaging it up into easy-to-use tools, or does it need to be some kind of service solution? This is really what the project is aiming to find out. So we're at this point, just to be very clear, we're not selling anything. We don't have anything to sell. We're going through this exercise to try and understand what might be the way forward, really, to ease the path for adoption of some of the things that we're talking about. So, what are we talking about? Well, let's look at this in terms of a system delivery challenge, and what we see as the core challenge in delivering distributed shared resource systems that deliver satisfactory performance at reasonable costs is how can they be made feasible and sustainable, and how can their tail risks be constrained? When we say tail risks, we mean the things that typically don't manifest until some time after something has been deployed. So what we're talking really is about how to manage the various constraints on system developers, and they're some of those are what we call cosmic constraints. They come from the laws of physics. Some are ludic constraints, and they arise from the way we've constructed systems and how various games, sometimes games of chance, get played out, and ecological constraints, which is really to do with the whole ecosystem of vendors and suppliers and so forth, and the constraints of what's available, what do you have to work with. So, system delivery challenge, right? What's creating this challenge? So this is going to be pretty familiar to most people, I should think, but just to kind of get it out there. So we have system requirements coming in, and that's fine. The problem with those requirements is they're quite often vague or contradictory, and of course they may frequently change during development, so that often causes a lot of problems. We have complexity, and some of this complexity is arising because we need to decompose our system hierarchically, and we may not be able to deliver the whole system ourselves. We may have to subcontract parts of it, or buy it in, or use third-party services and so forth. We're always working under time pressure. Time pressure forces us to develop things in parallel that would more logically be developed in some kind of sequence. So problems that we can run into are a result of having to kick off strands of work which are bound to interrelate, but in ways that maybe we can't foresee at the beginning. And the other consequence of time pressure is when we run into tricky problems, the temptation is very much to, rather than kind of slowing down progress in order to tackle them, we often push them to the end, and these become those tail risks I was talking about earlier. And then we're always operating under cost and resource constraints. So what are the consequences of that is to force us to use to share resources both within the system and with other systems. It also may force us to use pre-existing components that may not be ideally suited, either commercial off-the-shelf or third-party components, or things that we developed previously for some other purpose that we're reapplying to this. So to be a bit more specific, what does this challenge consist of? It's one key aspect of it that we're dealing with today is how to specify and verify the subsystem requirements or acceptance criteria, or if it's something that's been subcontracted or bought in, to do various things. So one thing is we want to meet, obviously, our functional outcomes. It has to do the right thing. It has to meet performance outcomes. It has to do the right thing sufficiently quickly. And pretty much any system that we think of has some kind of performance constraint. They may be very lax, but there comes a point where users lose patience and they just give up on something. And we have to meet resource constraints. And at the same time, we want to minimize the amount of integration testing we have to do and rework of things that we've done already. And we certainly don't want to get into a nasty cycle of reworking and then testing and finding new bugs and reworking and so forth. That's kind of development hell. I'm sure we've all been there. And at the same time, we want to manage risks. And risks can be to do with, for example, peak loads. They can be to do with post-deployment scaling of a system. It's all too easy to have something that works in the lab, and then as we start scaling out through pilot trials and so forth, things come out of the woodwork which we hadn't expected. So, obviously there are ways of dealing with this kind of thing. There are established approaches. There may be reasons why some of these approaches which are in use today are actually running out of steam. So to see what that might be, let's consider two dimensions of this problem. So the first is to what extent resources for the system under concern are dedicated to that system and to what extent they are shared. That's a dimension which is becoming increasingly important. And the other dimension to consider is to what extent all those resources are centralized and to what extent they're distributed. And obviously we're moving into an increasingly distributed world, and that brings its own problems. So let's consider some examples. If we think about something like a standalone microcontroller, for example, that has dedicated resources and they're all in one place, attached to the microcontroller itself. That's one corner of the problem. If we think about traditional mainframes, not so widely used these days, but still going, these are very centralized, ignoring for the moment the fact that the mainframe has internal structure and I/O subsystems and so forth. For the moment, just think of it as something where everything's in one place. But now we're running some kind of time-sharing system, and we're obviously sharing the resources of that mainframe between many users, different batch jobs, the operating system itself, and so forth. So if we're thinking now about traditional avionic type systems, they are distributed, that obviously they have to have components throughout the airframe, but the typical way of building these things is to construct individual black boxes, if you like, each of which performs a specific function using its own dedicated resources, connect them together with wires of some description, again, which are dedicated to the purpose of connecting those particular components, and that's the way these systems are constructed. We're shifting now into a world where, in the area of avionics, for example, where it's becoming cost and various other commercial requirements are leading to having more sharing of resources. So rather than having dedicated pieces of hardware for each function, that's going to having individual software modules running on some kind of shared platforms, and there may be several of those throughout the airframe, and they'll be connected by some kind of network links, and those links themselves may end up being shared, and connecting different software components in different bits of the hardware with some mechanism for sharing those transmission resources. If we think about a classic client-server system in an enterprise, for example, that's somewhere in the middle. Obviously, there is a lot of sharing of resources, but on the other hand, they are all under the control of the IT department. They're obviously distributed, but not necessarily beyond a building, or certainly not beyond the enterprise's own LAN WAN infrastructure. And then finally, we have the bright new world of cloud apps, where obviously these are distributed. Frequently, we may be doing some kind of mashup of applications which may be running from processors in different data centers. Obviously, we as the clients of these apps are separated from them, and these applications will be running in some kind of data structure infrastructure in a system where resources are being shared, everything's virtualized and so forth. So this is the kind of spectrum we're dealing with. Interestingly, when we think about IoT, that's basically linking the bottom left and the top right of this picture. Because we have kind of little embedded devices all over the place, but they're all connected to cloud apps. That's a very interesting challenge. So in this picture, the difference is as we go from the bottom left to the top right, we go from very constrained performance hazards. It's relatively easy to design and test these things to make sure that they meet their constraints in the bottom left, and very hard to do it in the upper right. And the general tendency driven by cost and convenience constraints is to move in that direction towards the unconstrained performance hazard. So that's, I think, is driving a lot of the considerations that we're dealing with here. Okay, so remember, if you have any questions about what we've done so far or comments, then feel free to type them into the question box that you have there in your control panel. I'm going to dig a little bit deeper into this now. Okay, so the core of this webinar really is to explore in a bit more detail some of the dimensions of this challenge. And we're going to do that via this diagram. This is obviously fairly complex and there's quite a bit in it. So we're going to take this a bit at a time. So let's start with this. The key task with shared resource systems and making something distributed really just has the effect of making the communication between the components of the system also something that's shared, is to find a way of quantifying and managing the performance resource trade-off, and that's what we're representing by this yellow section in the middle. And that's what that is, how that works exactly is going to be specific to each system. But the issues around it are the ones that can be dealt with in relatively generic ways, and so we'll talk about what those are. So really what we have is there's an analysis of the central problem which is complemented by a synthesis of a variety of other techniques. So there's three key aspects now that we want to consider in relation to this this trade-off between the outcomes that we can deliver and the resources that are being consumed. So the first is one of scale and how that trade-off is affected by the scale of the system and the way we want to scale it up. The second is how we deal with exceptions and failures. I'll say a bit more about what we mean by that, but basically as systems get bigger, as resources get more shared, just assuming that everything will work correctly all the time is really no longer an option. So that's something that has to be dealt with. And then the third is variability, which can be variability of the resources or variability of the demands on the system. Okay, so we'll take these one at a time. So let's look first of all at scale. So scale itself breaks into two main aspects, which we can think of as being space and time. So when we look at the scale in space, that can be to do with number of users, for example, effectively number of different demands on the system at any one time. It can also be to do with distance. Again, when we're talking about distributed systems, the other aspect of distribution is one of time. We're building systems that work at the speed of light, which sounds pretty quick until you're dealing with millisecond responses and so forth, and light doesn't get you too far in a millisecond, unfortunately. So these are aspects that need to be considered, and they come together in a notion of density. For some kinds of systems, the kind of density of use becomes a driving factor for how the systems are constructed and deployed, and may have a major impact on the economics of delivering whatever that set of services is. So thinking about time now, we need to think about the impact of various timescales. So on the longest timescales, we're thinking about questions of capacity. Do we have enough resources to deliver all the things we need to do kind of on average over long timescales? But as we think over shorter timescales, we have to think more about our capacity to meet all the outcomes, to do all the things that need to be done over a short period of time. Like, can we schedule our activities to meet the various constraints that we're dealing with? So we call that schedulability, and that in many cases becomes the key constraint. So thinking a bit about exceptions and failures now, when we say this isn't necessarily just to do with coding mistakes or hardware faults. We can think about things which are just a natural consequence of the sharing of resources. So for example, if we're using a packet switch system to communicate between components of our system, it's possible for a packet to get lost. That's just the way it goes. So there's really two ways we respond to something like that. We can either mitigate it. So if you think about a lost packet, we might use a protocol like TCP to detect that loss and resend the packet. Alternatively, we can propagate these failures. We might just say, oh, we've lost a packet, we're going to give up on this transfer. A whole transaction has failed. And that then becomes mitigated at the next level up. So mitigation and propagation are closely entwined, and the question about where is the optimal place to handle these things depends very much on the frequency and severity of these exceptions, and the costs of handling them in various ways in various places. So that can be quite a complex issue. So then moving on to variability, the key aspect of this is one of correlation. So when we have variations, they can be positively correlated. So this is the kind of thing that in the UK, the national grid, but whoever is responsible for dealing with delivering electrical power has to deal with when there's a break in some major sporting event which everybody's watching live, and suddenly everybody goes to make tea or coffee or whatever it is they need to do, and there's a huge correlated load on the system, and the same thing can be an issue with ICT systems. Alternatively, we can have negative correlation where, for example, if we have a system that can do several different things, but any individual user will only be doing one of those things at a time, then obviously those different outcomes are now negatively correlated. More of one definitely always means less of another. Or they can be uncorrelated, where this is just some kind of random effect that we just need to take account of. And these correlations can be externally created, like the power supply example, or they can be self-induced. They can be a result of the operation of the system itself. So the fact that it offers a set of different options and only one can be taken at a time is something coming from within the system, which is in that case causing a negative correlation. So when we think about all of these things, we need to think about their impact on the outcomes that an individual user or consumer of the system is experiencing, and we also need to think about their impact on the system itself and its ability to deliver the whole collection of outcomes that it's trying to service at any one time. So that's our kind of synthesis of the whole problem. But the key point we're trying to make here is that once that core aspect of what is the trade-off between the consumption of resources and the delivery of outcomes for the system in question, then these other dimensions can be addressed in basically generic ways, which you know we'll give some more examples of in the second webinar. So, assuming that's made any sense at all, here's a question for you. So, the question is, to what extent do the tools and techniques you currently use in whatever your role is, or that the organization you work for uses, enable you to satisfactorily manage these kind of issues? And we'll do this in a scale of 1 means not at all, and 5 means completely. We've got it completely under control. So here's the poll. Hand that over to Christian now. Give you a few seconds to give that some thought and click one of those buttons.
There we go. I can see the results coming in now, thick and fast. Excellent. We'll give you another few seconds to finish the voting in the poll. So if you haven't voted yet, please do come back and vote. And I will be ending the poll in 3, 2, 1. Give you an extra second. Here we go. And then I will broadcast these results. Over to you, Peter.
Okay, so the results of that poll give me some encouragement that we're not wasting our time here. Obviously, we've got a somewhat self-selected audience. You all decided you were interested in this, but yeah, that's our impression, is that not many people are currently in a position to completely manage all of these issues and the way they interact. Okay, so we'll talk a little bit about how this can become a practical methodology. So really, this needs to interact with a system development lifecycle. So it needs to support various stages of that. So in design, there's a whole question of feasibility analysis. There's supporting a reasonably optimal hierarchical decomposition of the problem, and constructing these subsystem requirements or acceptance criteria. When we come to verifying an implementation, we need to we need ways of checking the delivery of quantified outcomes. We need to be able to evaluate the resources which are being used, and this is something that needs to be something that's cheap to reapply during the system lifetime. So in fact, both of these stages, we talked earlier about how system requirements have a tendency to change over time, but other things can change, like the intended scalability of a system, or the number of different things it needs to support, and so forth. These tend to be moving targets, and the ability to rerun aspects of this design and verification cycle to check that nothing's going to be too seriously broken is going to be important. And when we look at validation, there's the question of how can we quantify performance and indeed resource usage criteria, and how can we check their coverage and consistency. So have we captured everything we need to know? And then out of that, we need to quantify hazards. So what is the risk of failing to meet requirements on delivering outcomes of some sort? So there's maybe due to physical constraints, schedulability constraints, as I was talking about earlier, or indeed supply chain constraints, that the kind of material you have to work with is perhaps not optimal for what you're trying to do. And then failing to meet resource constraints is typically due to problems with the way the scaling goes, or in the correlations of a load. So the key point here is to establish quantified intentions. So what is it that's wanted, and how can we quantify that? Because only by quantifying it can we then apply a rigorous methodology for being able to calculate whether those intentions can be met. And that's for outcomes and resources and for other costs. Once we have quantified intentions, then there's a variety of mathematical techniques that can be applied, queuing theory, large deviation theory, something we've developed and used ourselves called the delta Q algebra, So a slightly kind of humorous assessment of this is from our perspective, this is only rocket science. Now, of course, rocket science has been the way of indicating that something's really hard. But actually, these days, I mean, rocket science used to be something you had to be a global superpower to engage in. But now, you only have to be a billionaire. Rocket science has moved to the point that actually it's sufficiently well understood that provided you've got enough resources to apply to it, you can do it, and you can get a handle on the hazards which you're dealing with. You can apply engineering processes, and you know it can be done. This is different from something like brain surgery, for example, where you're totally dependent on the individual skill of a particular person, and a lot of it's down to their kind of their gut feeling about the right thing to do, and outcomes are generally very uncertain. So, so our mantra here is it's only rocket science. So let's do another quick poll. This is about quantifying intent. So imagine a couple of technical scenarios. So somebody's asking for a new phone system, but the first is that they just say, I want a new phone system. And the other is they say, I want a VoIP system that will deliver an average MOS of 4.2, be able to handle 30 concurrent calls, etc., right? Okay, a lot of detail there. So thinking about the things you deal with yourselves, so on a scale again from 1 to 5, so that first scenario, which is a very vague requirement, is 1, and a very precisely quantified requirement is 5. Where would you place the requirements you generally encounter in your work in your field? That's popping up now.
Excellent. I'll give you another few seconds to answer the poll if you've not already done so. I'm going to end the poll in 3, 2, 1. Here we go. And here comes the results.
Okay, well that's fairly encouraging. I think it also matches what we saw from the questionnaire, which I'll talk about in a moment. Okay, so one of the key things here is about how to quantify the issue of timeliness. So one of the problems in dealing with outcome requirements is it's very easy to think in terms of rates, so that we need to deliver 1,000 transactions a second or whatever it is. But actually, from the point of the individual end user, they don't care how many other people's response outcomes you're delivering. They care about how you're delivering their response, and this is the tension that needs to be managed. So let's take an example here. Let's say we're talking about something like a video on demand system, and let's say we could somehow get the marketing department to specify how long it's acceptable to wait for the first frame of the video. So let's say 50% of the time we want it to come in within 3 seconds. We definitely want 95% of people to be served within 10 seconds, and nearly everybody to be served within 15 seconds at most. And maybe it's acceptable to have a 0.1% failure rate where the thing just doesn't start at all. So that's some quantification. We can capture all of that together in a diagram like this. So we're looking here at a cumulative distribution where we've got the outcome response time on the bottom, and then effectively the probability of achieving that outcome up on the left-hand side. And the thing about having a requirement captured that way is now we can actually tell whether or not we met it. So in this picture we've now got a black line as well, and let's suppose that's actually the probability distribution. In this case it's the cumulative distribution function that the system's actually delivering, and that could be as a result of measuring the thing that we built, it could be a result of simulating the thing we're going to build, or of analyzing it using the sort of mathematical techniques we were talking about. And you can see in this case the black line is above and to the left of the requirement curve, and that is success. That is actually a unambiguous statement that the timeliness requirement for this outcome is satisfied. If that weren't the case, if the black line kind of cuts the blue line or goes below it, that's saying that there's a performance hazard. Right? There's a significant chance of not meeting the requirement that we started with. So that's just a taster of the way that we move into dealing with some of these problems. We'll have a lot more of that in the second webinar. What I'm going to do now is just feed back to you a bit of what you've told us already from the questionnaire that we sent out, which some of you have kindly filled in. And hopefully this will be of interest because obviously you will all know what you said, but this is what everybody said. So I'll just quickly run through some of these things. Fields that you work in, you were allowed to tick more than one box here, so this adds up to more than the total number of responses that we had, but quite a few working in the telecoms field in infrastructural services or indeed cloud services, and then a good spread of other areas of concern. Most working in the area of system design or architect, or the capability development and research, and a good spread across the life cycle. And actually we were quite surprised to see some of our respondents saw their responsibilities as stretching across a wide range of this, or even the whole of this system development life cycle. And when we asked the question about where do system or product requirements come from, interestingly, they rarely come directly from the client or the customer. Quite a few of them are derived in collaboration or generated internally just using experience and engineering judgment. Some of them come from standards, and some are developed using, basically they're more of a kind of marketing-led thing. They're derived from an expectation of what customers are going to want. And then we asked the question to what extent these requirements are precise and unambiguous, and nobody said they were completely imprecise and totally ambiguous, but quite a lot of people thought that they could be a lot sharper. But interestingly, when we asked whether they were quantifiable or quantified, we kind of got the opposite picture. That the tendency is to say that yes, they are quantifiable or may even be quantified at the same time as being not very precise and somewhat ambiguous. So there's an interesting tension there which we can maybe explore a bit more as we go along. So we asked the question how to determine whether requirements have been met, and there was some spread here. Quite a heavy emphasis on feedback after deployment by waiting for complaints, but at the same time also there are test and integration steps which can either be done informally or with some kind of formal sign-off procedure. And sometimes these things are just done informally by demonstrations. And the response to a discovery that requirements haven't been met or won't be met is interesting here. This is suggesting that there's a lot of exposure. A lot of organizations, a lot of you say that this will result in redesign or rework at your own cost. So that suggests that there could be some appetite for approaches for mitigating these problems and dealing with them earlier in the design cycle. And a lot of you are concerned with both overall performance and its impact on individual users, as shown by the pie chart on the left. When we take some averages of responses on the table on the right there, performance is seen as pretty critical to success. You yourselves are pretty accountable for it, but not in very good control of how resources are being shared. So there's clearly some issues there. And there's quite a lot of concern about the effect of that resource sharing, perhaps not matched with the extent to which there's any control or influence over how those resources are shared. Okay, so I hope that quick trot through the results we got from the questionnaire is of interest. I'll just quickly sum up now. Remember, think of some questions because we've got some time at the end coming up to address questions or clarify things which I've run over. I've gone over this pretty quickly. So if you have some things to ask, remember to type them into the question box there. Okay, so just to sum up now, we're envisaging an approach, a more quantified, more mathematically based approach to handling this issue of delivering quantified outcomes and managing the sharing of resources and the cost of the system. So in ways that would avoid infeasible developments, enable things to fail early if they're really infeasible, or to prune blind olives of directions of development which are going to turn out to be infeasible. To address issues of scalability early and pull in real-world constraints, particularly things to do with distance in distributed systems, and avoid a kind of heavy tail of hazards that mature late in the project and cause delays and overruns. And have a way of seeing the whole risk landscape, not just the first problem, so that resources can be deployed effectively to deal with the most dangerous problems from the point of view of the project, rather than just the ones which crop up early on, and potentially be able to write a safety case. So this is not something which concerns many parts of the industry today, but what we're seeing is a push to reusing or repurposing standard kind of commodity infrastructure for safety or mission critical purposes, and that obviously has tremendous economic benefits, but it also brings considerable risks if it's not possible to write the safety case for systems that use shared resources, whether that's data centers or packet networks or mobile radio networks and so forth. We need to find ways of analyzing that so that actually safety cases can be constructed. That all sounds great. Obviously, nothing comes for free. There are costs of doing all this. One is the need to quantify intent, which in our experience, and as we've gone through this, we've done some case studies already in the PEnDAR project, that may be difficult and it may meet resistance. The client who just wants a new phone system is like, just go and do it. Stop asking me all these complicated questions. There's obviously effort in adopting any new tools and techniques, and there's a problem that's already faced in the area of functional verification and validation, is that it tends to cause a lot of upfront work to occur. In terms of capturing and quantifying requirements and formalizing all this. All needs to be done before anybody starts writing code or building hardware or whatever it is. Most people in the kind of engineering field know that that's the right way to do things, but from a kind of management perspective, that may not look like progress. So there may well be pressure to kind of kind of get past all that and get on to doing something, building something, showing results. So these are all issues that we're aware of, and there may well be others. If you can think of others, then please let us know, because that's what we're hoping to get out of this exercise. So next steps in this process is we're going to run another webinar on the 15th of March, and you'll get an invite to register for that if you're hopefully interested, which is going to be an outline of what is this methodology we keep talking about. Obviously we're not going to go into too much detail, but we'll kind of dig down another layer from where we've been today, and provide some quantitative worked examples of some of the steps. So we're not going to be able to analyze a complete system, but we can show how, give some examples of how particular aspects of this methodology work in practice, and how this relates to challenges in the ICT field. For example, virtualization, which is starting to bite everywhere, not just in apps and data centers, but in provision of network services as well. After that, we're going to be doing some interviews. So it's an opportunity. This is not something we're necessarily expecting everybody to do, but for those of you who are particularly interested, we'll conduct some one-to-one conversations to provide us with more detailed feedback. And then we've got a third webinar in May, which will give the conclusions of the project and really what we've learned from this whole process. And we'll be putting out a survey at the end of the project for, hopefully we'll have learned through this process the questions we should be asking, which may not be the ones we asked in our kind of opening questionnaire, in order to get some more detailed feedback that we can take away and chew over. Okay, thank you. This is now the time for any questions that have come through. Christian's put the link up already to register for the next webinar. So, do we have any? I know it's always a challenge to come up with something kind of on the spot, but if anybody has any questions right now about the content of this webinar, where we're going.
We have one question from Roger Shepherd. To what extent can the new methodology clarify requirements without having to perform experimental implementations?
That's a good question. So the point here is to effectively quantify the requirements independently of an implementation. So there's always, I mean, we're always trying to walk the line between what people would ideally want, which is kind of everything everywhere for nothing, and what it's actually practical to deliver. But I think if you can get to the point of at least having a view of, okay, this is something that we think can be delivered, then the question can be asked of what does an acceptable delivery of that look like, and that may be a question. It may be a kind of subjective question in terms of actual people interacting with it, but it may be something that it's more. It can be quantified from external source. So if we're building a system that's, let's say we're trying to run GSM small cells, right? 4G, 5G small cells, whatever they are, and we're trying to create a network service which is satisfactory for running those small cells. We can quantify the requirements of the transmission to the cell kind of independently of what the network is actually able to deliver. So it's not a question of building it and see if it works. We can say, well, actually, in order to work, it has to meet this timing requirement, and it has to be able to deliver these particular messages within these time constraints and so forth. That's the kind of thing that one can quantify in advance of building your trial implementation. So I think the intention here is to find ways of capturing and quantifying requirements which can then be tested against a conceptual implementation as opposed to necessarily an experimental one. I think Neil wants to add something here.
Yes, it's actually possible to, and we have done this in a few cases, to do it entirely algebraically. So it is possible to start off from a set of requirements and work out the constraints without ever, yes, you have to write some mathematics and you may have to simulate the mathematics with Monte Carlo methods, but actually you can end up with a quick answer of feasibility that way.
Okay, thanks, Neil.
And then we've got a couple of questions from Gavin, if we have time.
Sure, yeah, I think we've got a few minutes.
Okay, so should we start with, do you see any particular industries/sectors much better than others in terms of effectively quantifying intent in requirements capture?
That is a good question. I would say, so if we think about something like avionics, for example, that's going to be a field where most of the requirements are going to be pretty well quantified. It's going to be, when this happens, we need to move this flap within this period of time. That's going to be a pretty well quantified requirement, which is basically coming from the mechanical system that we're dealing with, and that may be true for a lot of IoT applications as well, for example. On the other hand, when we have something which is where the requirement is kind of more fuzzy, it's like we're doing some kind of web app, and how quickly do we have to render this page for the user to be satisfied? Well, then it's becoming more of a kind of social science problem to quantify that requirement. It's not something you can do just with engineering. It then becomes a matter of you're trying to measure people's happiness and satisfaction with the delivered service, and that gets a lot harder. But the sort of thing you can say there is what you might find is if the user gets some kind of response from the system, like we're working on it, we're making progress within a certain period of time, even if they don't get the full answer until some seconds later, maybe that makes them happy. But you need to start employing psychologists to do that kind of quantification. So I think where you've got these kind of cyber physical systems and the constraints are coming from the physical and mechanical aspects, the quantification is going to be a lot more straightforward than when you have purely digital systems where you're just delivering some solution to kind of human end users. That's generically, I would think, the kind of spectrum that you're trying to deal with. I think Neil may have something he wants to add.
Actually, I was going to answer Gavin's next question, which is about is there a difficulty in getting people to quantify this stuff in a statistical format? It's difficult to get them to think initially that they may not be perfect, but once you've got them to think and they realize that there's a value in them defining something a bit more quantified, i.e. there's a zero that can disappear off the end of the bill if they basically trade a 0.1% of the delivery time, they do get very engaged very quickly.
I think Lucy's going to add something as well.
I would add to that people don't think they have specific requirements, but often if you have an off-the-shelf requirement for people, they go, oh yeah, no, that sounds fine. So sometimes you have to give people a chocolate box of options, and they can be like, oh, I like a caramel better. So when we used the VoIP example earlier, a lot of people don't realise that they could ask for such specific stuff, and so they don't try to. They don't even realise that it's a thing. But if you just said to someone, we could sell you a VoIP service that comes up to our standards, and you have like a standard version, a lot of people would just say, yeah, I'll take that, and then you can find out whether or not they're happy with that. Sometimes you just have to suck it and see. But I think we've got no more questions, so Peter, would you like to wrap up?
Okay. So thanks everybody. I hope this has been interesting. I hope you'll sign up for the second webinar, and we've certainly enjoyed presenting this, and thank you for coming. Okay, hand back to Christian.
Thank you so much, everybody on the presentation today, and thank you so much for our participants for taking part and for your great questions at the end of the session. I've pasted into the questions box there the link to register for the second webinar that's on Wednesday the 15th of March. So please do click on that link now and go and register, and we will see you again on that webinar. So thank you all again one more time. I'm going to end the webinar now, and we'll see you in March. Bye-bye.